on, the detectors push them out. Fragmentation 1.7 volts looks like this. Okay? So it's the distance moving to the rods. Okay, now, the question is he moving in a vacuum? Is the trap in a vacuum, or is the trap filled with something? It's filled with helium all the time to a pressure of about 1 millitorr. So those ions are not moving in a vacuum, they're moving through a bath of helium. It is just like a child playing in the tub with a toy. Okay, the water density is almost about the same visually. Okay, from the ion's point of view. So the minute he starts moving back and forth, he's colliding with the helium. Okay, so let's now go to the molecular level. Take a peptide which weighs, let's say, 1,500 daltons. Collide it with a helium which weighs what? 4. What happens when the peptide collides with the helium? Does the peptide fragment?
If it's enough energy.
No.
Just slow down a little bit.
Right. What happens to the helium first? Let's take the helium first. What happens to him? He goes flying. Some of the kinetic energy from the peptide is conferred upon the helium. He goes flying. Is that energy transfer process 100% efficient? No. We know from physics that no process is ever 100% efficient. So where does some of the kinetic energy go? Into the peptide itself, the ion. What types of internal energy can we have on an ion? Vibrational,
Stretching.
which is vibrational, rotational, and electronic. Electronic is spectroscopy. Rotational is molecular spectroscopy. Vibrational is mass spectrometry. Okay. So that kinetic energy, a small percentage of it goes into the molecule and he vibrates. Now, has he lost kinetic energy? Yes, but he's still within the same electrostatic field that he was at the initial point. So what happens to the energy he lost? It's immediately replaced because he's in the same electric field. He comes right back to the same energy. He now collides with another helium. What happens? He gains a bit more vibrational. After about 10,000 helium collisions, which at 1 millitorr takes a time of about 1 to 3 milliseconds, he's gained enough internal vibrational energy to overcome bond energies. And when you overcome the bond energy, that means you're moving the atoms to infinite distances apart. He fragments. Okay, now, do all bonds fragment?
With enough energy.
With enough energy. Do all bonds make fragment ions in a trap? Just primarily the amide bonds plus a few other bonds occasionally. We definitely don't see side chain fragmentations and all that. Okay, just the phosphates, which are very peculiar. Okay, now, why do some bonds break and other bonds don't break? There's 3 things. It's the lowest energy bonds that can vibrate. Can all bonds vibrate equally well? No. Right. What kind of shapes vibrate well? Dumbbells. What kind of shapes don't vibrate well? Rings. Peptide bonds are great because you have this weak single bond with these big weights on the ends. So it's the lowest energy bond that can vibrate and localize the energy. But you don't want the energy over the whole molecule, then you get an explosion. You want the energy at a bond building up, and then you get a nice break. Okay. Cool? Now, the minute the bond breaks, what interesting fact to a mass spectrometrist changes? Think simple here. Interesting to a mass spectrometrist.
It makes 2 different sizes.
It makes 2 different sizes, 2 different masses. What interesting to a ion physicist changes? Physicists don't care about mass, they care about frequencies. The minute that guy breaks, the new product ions have different masses. Hence, they immediately undergo different frequencies. Do they match the dipolar? No, so that's why they don't refragment. This is why all bond breakages we see in an ion trap are one event processes.
So they collapse down to a small...
And they cool right down, yes. Okay. This is why we don't see products of products. All our products are one generational.
Unless oh no, the fragments would always be small.
Right, okay. Cool. Now, phosphos, which is what you guys are interested in, are very peculiar. They're very labile, okay? When you shake...
The non-conjugated tyrosine phosphos are not.
Now there's an interesting thing.
Because it's conjugated.
Do you see tyrosines undergo the neutral loss?
Sometimes, but it's not nowhere as potent as this.
Yeah, this is interesting because Hunt originally said phosphotyrosines don't undergo the neutral.
You see. Yeah, you see.
Insulin receptors are beautiful phosphotyrosine. Neutral loss is great.
Yeah, minus 80, you see.
Okay.
But it's usually minus 90.
So there's an interesting work by Sue Weintraub. You know Sue Weintraub, San Antonio Health Sciences?
Yeah.
Sue did a whole bunch of synthesis of just changing one amino acid.
Yeah.
And she didn't make it official, but she showed some data that it seems like there has to be an acidic residue in close spatial proximity. And then the phospho undergoes the neutral loss beautiful. So serines and tyrosines especially. The serines and threonines, they always seem to neutral loss pretty much. The tyrosines, if there's an acidic residue nearby, they seem to undergo the neutral loss beautifully. Okay, so Sue, she said she didn't have enough data to make a definitive yes, no, but she goes, it seems to be that the acidic residue helps the tyrosine to neutral loss. Okay. So those are very peculiar, interesting. That's the only, you don't look at glycos, do you?
No.
Okay.
Phosphorus enough.
Yeah, glycos are, I did a week of those recently. That just gives me a headache. Now, I want to mention the future, which is very interesting.
So they really are serious about ETD on the FDA?
Yeah, we're
because you're going to kill your market if you don't do that.
Unlike Brooker, though, we didn't announce it a year and a half ahead of our release date. We don't like to until we have something actually working.
So you're trying to feed this beam of small chemicals into the side instead of the back.
Yeah, and
they got to get that working.
People think Hunt had it all done, and he got a lot of it done. There's just still, to commercialize an idea is a lot of work. I wanted to come to a picture that went too far. So ETD's coming.
Do you guys have a trademark on the other companies going to do ETD?
Brooker announced it already.
So it's not like, so basically Hunt is Hunt?
I don't know how. He's a collaborator of ours. I don't know how that collaboration thing I just don't understand. So I just keep my nose out of that one. But I do know that they're working on it in San Jose. Yeah. But it's just not, it's not as straightforward as people think. Okay. ECD on the FT is really because you don't have to go into the...
It's a beam of electrons because it's a lower back.
Okay. The ion trap, you actually have to go into the trap and do some funky things. And the thing is, right now we sell most ion traps without a demo. Okay, so we're very scared to death to release something that doesn't work well or is not completely understood. And that's what we just want ECD to go out and be a simple thing. We don't want ECD to get out there and ETD and everyone's like, oh my God, did you think about this, this, and this? And look we're scared. What I want to mention is PQD. Did you see this? You saw that's the one you were asking about, the eye track. Did you see the talks at ASMS?
I wasn't able to.
Oh, okay. I want to talk about this. This is coming. We hope very, very soon. I don't give a date because I don't believe San Jose dates until I actually see the product in my hand. When we fragment ions, we put the precursor at a Q of 0.25. Okay, that's a choice we make, and it has to do with the following science. We want the precursor as low as we can, because if he is here, then I have this whole region to create product ions into. Okay? When I take him up to a Q of 0.25, see how my hands kept the same distance? Right here is a bunch of product ions created that are instantaneously unstable, and the small ones we lose. The minute they form, we lose them to the rods, to the